Good morning, everyone, or good afternoon, depending on where you're joining from. Welcome to our webinar. My name is Alan McKee. I'm the Communications Specialist for CANU, which is the Canadian Urban Environmental Health Research Consortium. I would like to start by acknowledging the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. Before we get started, I'd like to remind you to please turn your cameras off and stay on mute during the webinar. Please put your questions in the chat and we'll have time at the end of the webinar to answer them. It's now my pleasure to introduce our speakers today, Jeff Brook and Aaron Van Donkelaar. Jeff Brook is a scientific director of the Canadian Urban Environmental Health Research Consortium, as well as assistant professor at the Dalla School of Public Health and the Department of Chemical Engineering and Applied Chemistry at the University of Toronto. He has 25 years of experience as an Environment Canada scientist working at the Science Policy Interface, and he is one of Canada's leading experts in air quality, recognized at all levels of government and academically, including for his substantial contributions in air pollution health research. Aaron Van Donkelaar is a research associate with the Atmospheric Composition Analysis Group at Washington University in St. Louis. His research combines satellite retrievals with chemical transport model simulations to estimate fine aerosol concentrations around the world. This work is being used to provide valuable insight into exposure-related health effects in regions where these concentrations are not monitored directly, which includes some of the most heavily populated and polluted places on Earth. So we are very grateful to have the opportunity to hear from both of these researchers today. And with that, I will turn it over to Jeff Brook to start us off.
Thank you very much, Alan. Pleasure to be doing this with Aaron today. Let me know when you can see it on the screen, Alan.
Yeah, we can see it now.
Okay, great. Well, today is an opportunity for us in CANU to talk about air pollution and particularly PM2.5 or fine particles. It's not very clear to me who might be attending and what your level of knowledge is for PM2.5, but I thought prior to learning about the work that Aaron has been doing, I would provide some background on PM2.5 that may help to bring some people onto the same page and appreciate more some of the challenges that exist in working with this important air pollutant. You just heard Alan talk about Aaron's work in fine aerosols and PM2.5, which stands for particulate matter smaller than 2.5 microns in diameter. It's often also called fine particulate matter. I think rolls off the tongue easier for me to call it fine particles. Today, I just want to give a brief introduction about why it's important, more about what it is, and talk a little bit about some of the long-standing scientific and policy challenges, particularly in regards to studying PM2.5 effects through epidemiological research. But more importantly, I want to warm you up for today's main attraction, which is Aaron Van Donkelaar, who's had huge impacts nationally and globally in this whole area. Now, just to start off, I put up here a summary plot from the latest paper in The Lancet from the Global Burden of Disease on various risk factors for mortality. And these analyses continue to show that air pollution, which is a lot of it in these analyses due to fine particulate matter or PM2.5, is right up there near the top in terms of major risk factors for mortality on a global basis. These are two graphs separating them by male and females. But you can see here air pollution in terms of numbers of deaths in thousands globally, where it stands number 4 in this latest paper that corresponds to quite recent years, 2019, for the analysis of the data for both males and females. And the light blue bar indicates cardiovascular diseases, and that is one of the main outcomes from which fine particulates have their effects. But there are a number of other impacts that you can see in this analysis that it also has. I mentioned that ambient PM2.5 is the major pollutant responsible for this bar in this analysis. There is ozone included in here as well in terms of its effects, respiratory effects on COPD, and also for some countries, household air pollution. Burning of solid fuels is another source of particulate matter and air pollution that leads to very high exposures for many people in the world. These are combined in this latest analysis, reflecting, I think, in one way, as we think about it, the fact that these small particles which carry mass and are inhaled are having the same effect regardless of sort of where they come from. They're all right now seem to be sort of equally toxic and leading to this very large effect. From my own perspective, I also like to point out that we see that up the curve in terms of risk factors is high blood pressure. And we also know that if we study the development of chronic disease, that PM2.5 plays a role in the development of hypertension. So there may be even some additional effects if you're to try to attribute some of the hypertension back to air pollution. Very difficult to do. We're looking in Canada, this recent analysis that actually is fully enabled from the type of work that Aaron's done with satellite maps. We've found that looking at the most recent WHO guideline, which was just put out in 2021 and cut the annual average standard in half from 10 down to 5, reflecting the latest health knowledge. I find that 86% of Canadians are living in areas that are still above this annual average of 5. 5 is almost background, but not quite background air pollution, which arguably is around 2 to 3 micrograms per cubic meter in Canada. This map shows areas in blue, populated areas in Canada blue, where people are living in areas where the PM2.5 is below the WHO guideline. The orange is areas where people are living that the PM2.5 is between the WHO guideline of 5 and the Canadian ambient air quality standard known as the CAQS of 8.8. So quite large areas would be in compliance with respect to the current CAQS, but not with the WHO guideline. And then the red areas are showing where in Canada we're having challenges with even meeting the current CAQS. There is 26 million people who are living in these areas that satisfy the CAQS, but are above the WHO guideline. So this really implies from the GBD analysis and the burden and the impacts and this analysis of Canadian levels versus standards that we still will realize benefits from further reductions in PM2.5 across the country. This comes from the WHO exceedances. It's also seen directly in epidemiological research in Canada, a lot of it done through the leadership of Rick Burnett and Michael Brower, with great dependence of exposures on the work that Aaron has done through the look at the Canadian census cohort, CanCheck it's known as, of which this includes 3 different time periods, which continues to find significant associations going right down to even background levels, as some more recent work that Scott Wickenthal has done with the project that Mike Brower leads. So we can detect the effects in the Canadian population in these large cohorts. We know that they're above what the experts who've advised WHA say is the current guidelines. But when we think about these very low levels, that's a big question right now, is are the effects at these low levels that we can observe epidemiologically robust? But then also, how could this be happening? What's going on there at these very low levels? Certainly globally, we know there are very high levels that we'll learn about from Aaron, but at the very low levels, what could be happening? I think that we still don't have the answer to that, but it's important for us to think about the multiple dimensions of PM2.5 that are there. It's not just a single entity of mass of one compound. I want to talk a bit about these multiple dimensions to hopefully have you appreciate more the types of data that Aaron are going to show. So the first dimension to think about is size. And as I mentioned, PM2.5 stands for the particle mass below 2.5 microns in aerodynamic diameter, which really corresponds to this little particle here relative to human hair. Or on this sort of little ruler here, we see the PM2.5 is really in around the range of the size of red blood cells or bacteria. When we measure PM2.5, we collect all of the sort of solid, semi-solid matter in the air that's below that size and essentially weigh it to get the measure of PM2.5. Now, this size is really important because smaller size particles do have more potential to get deep into the respiratory tract and carry a range of chemicals down that far where they can deposit and have impacts. But larger particles that we often call PM10 up to 10 microns, are also able to get down the respiratory tract. We also sometimes think about getting up into the size of 100 microns, which gets more into dust. And you can see sort of some analogies for different things that we can recognize. So size is one of the important dimensions to be thinking about. We are very focused on PM2.5 in a lot of research, but it's not the only size that's there, and it's also not the only size that has effects. Also, at the very, very small size, there's another sort of dimension that we call ultrafine particles that can be in the millions of numbers per cubic centimeter in heavy trafficked areas that you can see relative to 2.5. They're very tiny, and they're ubiquitous in our urban areas or anywhere near combustion, indoors or outdoors. Another dimension of importance is the chemical composition and the source from which they come from. And these pie charts are very commonly used to describe the composition of PM2.5. These are charts from recent data spanning sites in the US from the Pacific Northwest across through to sort of Southern Ontario, Great Lakes region, Northern New York. And it's broken down into sort of the predominant components that we often think about for 2.5. Ammonium nitrate. So when we say nitrate, it's bonded to ammonium to be on the particle phase. Sulfate, which could go from sulfuric acid to fully neutralized ammonium sulfate, but typically there is ammonium bonded to it. And then elemental carbon, or often called black carbon, it's the sooty blackness that's there that we see visibly in some emissions. And then a large fraction that is organic matter or organic carbon. And we can see that across this gradient from west to east, how their relative proportions do change. So PM2.5 is not the same everywhere. Its composition is dependent on the sources in the area, which could be natural or from human activities. I point out here that in the Pacific Northwest, this organic fraction is a large piece of the pie relative to the sulfate and nitrate. If we get into the sort of more central part of the continent, dust, where we do know there's lots of agricultural activity, comes up quite a bit in its size fraction, 26%. And then towards the east, where we're more downwind of things like coal-fired power plants, the amount of sulfate in the size of the pie increases. So composition varies spatially. It also varies, of course, day to day, depending on what sources are impacting. But one of the key features about PM2.5 that I think it's important for people to realize is that a good portion of it forms in the atmosphere. In actuality, the ammonium nitrate and ammonium sulfate originally came as gaseous emissions of sulfur dioxide and nitrogen dioxides, and then through forward chemical reactions become into the particle phase, sulfate and nitrate. So right off the bat, that piece of the pie, we would say, is formed in the atmosphere. It's secondary. Also, while it's not well known, the exact amounts, it's probably a safe assumption to think that half of the organic matter is also formed in the atmosphere, which means that 70% of the PM2.5 is formed in the atmosphere. It's not directly emitted in terms of the east area. And you can see if we do that sort of same assumption across the other areas where we stand, more than half, 50 to 70%, I think is a safe estimate of the PM2.5 forms in the atmosphere. It's not directly emitted. So this secondary formation is linked to photochemistry, to sunshine, and OH radicals, interactions in gas phase and in liquid phase in clouds that lead to the formation of those compounds. Another pollutant that we often think about is ozone, and that's also a photochemical pollutant. Given that photochemistry impacts ozone and impacts secondary PM and more than half the mass, we can very easily appreciate how half of PM2.5 is linked to ozone via photochemistry, meaning they can vary similarly in time and space. Looking at particles more closely, because these pie diagrams are nice to summarize things, but they really tell very little about the true nature of particles, which are very complex. And starting here, if I look at this particle and think about the other half of the particles, what we call primary, so directly emitted, it can come from many sources: resuspended dust, abrasion of materials, whether it be surfaces or tires or brakes, sea salt from sea spray where there's ocean in the area, or many different forms of biological matter, from leaf fragments to pollen fragments or spore fragments, all contribute. This is a picture here that shows sort of the complexity of soot, the elemental carbon, made up of tiny spherules formed in combustion that get into these sort of bunches of grapes type formats that we'll see under an electron microscope. That certainly would be a primary combustion related PM2.5 source. Fossil fuel combustion is a very important source, but also burning of wood, which could be for residential heating, recreation, or wildfires, very important. And a range of industrial processes will produce the primary PM emissions. But that's only part of the story of PM and how it looks. As it's emitted, it's never coming as this pure soot. It's always got things like tiny trace amounts of metals and organics that are embedded into this matrix, absorbed onto it, that increase the complexity. On top of that, as conditions change in the atmosphere, organics that may be in the gas phase sometimes, in the particle phase other times, can move back and forth and come on to, say, the surface of the particles, or even sometimes migrate into it, but certainly on the surface. That's what I draw this line there. On top of that, as sulfate and nitrate form through photochemistry, they will then condense onto the particles, creating further coatings onto this particle. And ultimately, water is really critical also in terms of coming onto the particles and swelling them to even larger sizes. You can sort of visualize this general complexity from this diagram. And literally, there are thousands of chemical compounds that can be found in particles. Many of them organics, things like polycyclic aromatic hydrocarbons are on there. But we also know that many of these are known to be toxic. And of course, we do know that diesel particulate matter and even PM2.5 is considered carcinogenic. So this is really kind of a cartoon showing the simplicity, the sort of, in a simple way, how complex these particles really are in terms of their makeup and their morphology. Now, another thing to think about is that they don't all look like this. Generally, we view them this way, as either being internally mixed, where all the different sort of chemical components are all on every particle that's floating in the air. But that's not always the case. They can come in what we'd call an external mixture, where each particle has got a different composition that may more directly reflect the source. So these are some important considerations to think about. And in reality, I think our simple conceptual model suggests that over time, we may start with sources emitting their own sort of unique particles. And then as it evolves over time, from hours to days to a week or more, they begin to come sort of into more a combination of the two, to ultimately further downwind as they age in the atmosphere to maybe more of this sort of internally mixed, more spherical type aerosol. And given this time also means movement with the winds in the atmosphere or vertically, suggests that as we move from near source areas to farther away, this type of mixture can turn into the external to the external pattern, meaning that there is lots of additional complexity in the spatial patterns in the makeup. we also can't forget that 95% of the mass that we breathe is actually coming in the form of gases. Things like carbon monoxide are very prevalent. Ozone, I mentioned earlier, volatile organic compounds, nitric acid. There are many, many gases that we're also breathing in every breath of air that come with the particles, although particles are unique in their ability to be carried deep into the airways and not potentially react in the upper respiratory tract as some of these other chemicals might do. Two important chemicals to think about here are ozone, which I mentioned earlier is photochemically produced through reactions in sunlight with volatile organic compounds and nitrogen dioxides, a photochemically produced oxidant. And often these photochemically produced or secondary pollutants tend to be more homogeneous spatially. They change more gradually because they last in the atmosphere longer than the primary pollutants, which are higher near the sources. The other pollutant I point out here is nitrogen dioxide. It's another pollutant that's very commonly thought about in research and exposure. It's very common in emissions from fossil fuel combustion. And we often think of nitrogen dioxide as a good indicator of traffic-related air pollution. So much research on air pollution health tends to think about these three pollutants, PM2.5, just as its mass, ozone, and nitrogen dioxide, and tries to think about their relative impacts in terms of their associations with health outcomes. Now, PM2.5, as I pointed out, because of it being primary and secondary, means that it will co-vary with ozone and with nitrogen dioxide. And it kind of tends to then carry the signal of its sort of variability in time and space of itself, but also is related to the variability in ozone and nitrogen dioxide, which if you had to measure one thing might have some advantages. So just to sort of wrap up quickly, if we're thinking about those three key pollutants, which are often what are brought into epidemiological studies, and then analysis might be done associating outcomes with a single pollutant and multi-pollutant effects or multiple things, the evidence is consistent worldwide that PM2.5, as this measure of mass below that size, has a range of effects. And that's certainly supported by not just association studies in epidemiology, but a wide range of different designs in terms of mechanistic biological studies or other studies looking at chronic disease. It is also because of its characteristic of being related to so many different sources and also related to NO2 and ozone, combustion, secondary formation, probably, in my opinion, the single best indicator of air quality that we have. And so it's really good to think about PM2.5 levels and really use it as a driver for improvement in air quality. Now, that's definitely the case where PM2.5 is high. As we get to lower levels, it becomes a little more challenging. But it's also important to recognize, while there are many sources, that recent work, led by Mike Brower and also the group that Aaron works with at Washington University in Seattle, is that globally, fossil fuel combustion is the most important source to address. It's estimated through this work globally that 1.05 million deaths in 2017 can be attributed to this source, fossil fuel combustion, contributing to PM2.5. But it's also important to realize that while this is a groundbreaking analysis that has done a great job at breaking out the sources of PM2.5 all across the globe, it's still in the burden estimates to get these numbers, is assuming that all PM2.5 mass has equal toxicity. Whereas going back to those complex diagrams, we know that's not necessarily true. And that remains now 20, 30 years of time that I've been working in this area, a question that's been not fully answered. Some of the challenges are really that as we try to do multi-pollutant studies and consider these three pollutants together, there are differences in the effect size of PM2.5, depending on whether you adjust for NO2 or ozone in your multi-pollutant analyses. And a lot of this really still remains unexplained as to why these effects happen, because there are differences in how this adjustment affects it depending on study. And that could be because of how they are interrelated and how they vary in space and time, which is not exactly the same everywhere geographically. It could be because of the differences in the composition of PM2.5, And there's growing work showing that that certainly that is the case. And if you take different particles and do toxicological in vitro or in vivo, we do see differences. So we know that that definitely is the case, but hard to crack into through epi. And there's also differences in the exposure error structures among them that make it also very difficult to interpret and get at the bottom line. In areas where levels are very high, I think it's just fine and really critical that we just use PM2.5 to continue to drive down levels and make improvements. But in Canada, where it's now very low and approaching the background and there are still effects, we need to start to think much more about these interactions and what they mean, and think more about what sources and what compositions and what components of the remaining PM2.5 we might want to invest in more to try to reduce the risk that we see. So I'd stop with this image, which is something that Canoe has just now been putting up onto the website for people to utilize. This is a multi-pollutant satellite-based index of air pollution based on principal component analysis. And these data are available for people to utilize and explore across North America. And it's combining in these components several pollutants together into one, to not think about really trying to separate them, but just what is maybe the total combined effect, given different ways in which they do covary. So I'm going to leave it there, and hopefully have plenty of time now for Aaron to continue, and then some questions. Thanks very much.
All right, so I'm going to carry on from there. So Jeff's done a really nice job of outlining why we care about PM2.5 and some of the existing questions and what it is. So I'm going to change gears slightly and talk about how we produce large-scale estimates of PM2.5, and specifically how our group does that using a variety of different data sources from satellites and monitors and models, both how and why we might want to do that. Then I'll spend some time basically walking through some of these data sets and some of the questions that might be worth considering if you're working with these data sets, different things to consider, how things have changed in time, and different factors might affect if you're looking to use this data for different studies. I'll spend a little while talking about some of our very recent data sets that we've released. This is an active data set, active area of research for our group. And so, every few years we come out with a new version, and we often get the question of, what's new? Should I upgrade? And I just thought it was worthwhile spending just a slide or so talking about what's new in the new version and how that might affect your research. And lastly, just spend one very brief slide just talking about sort of the impact that I'm quite thankful to have been a part of with this research, and the sort of impact it can have to this big data approach, bringing all these things together. So first off, why do we want to include satellites in air quality monitoring? As many of you are probably aware, ground-based monitors can provide a locally accurate representation of PM2.5 with a fairly high sampling frequency in many cases. And I should slightly nuance that. Of course, there are very different degrees of accuracy for different monitor characteristics. And of course, there's low cost or standard ones. And there is certainly some variability within that, but generally speaking, ground-based monitors can provide a locally accurate representation with frequent sampling. To get an idea how it may not be as simple as that in all cases, however, I've taken a few images here just of some ground-based monitors. One placed very clearly designed to focus the effect of traffic flow patterns, and this other one on the other side, obviously placed in a park somewhere where there's just trees around and not a lot of population, not a lot of sources that way, for at least anthropogenic sources. And so you can imagine how in this first case, this could be a very accurate and incredibly useful monitor if you're specifically studying traffic flows. However, of course, you can imagine that the concentrations it is observing may not be representative of what's happening, even 500 meters away. There's quite likely to be rather extreme gradients associated with that. And this is a very different situation than on the right-hand picture here, where without a lot of active sources around from anthropogenic, not a lot of spatial variation in those sources, quite likely that monitor is representative of a large area. When these represent two extremes where we have ground-based monitors, and a big challenge in using that data can be, well, how do we interpret that specifically for interested people? How do those monitors relate to where the population is and how they're actually exposed? On a more global scale, of course, you have another question entirely, which is how many monitors are there even on the ground, ignoring these more local effects. And to give you an idea of that, I've plotted here just an image showing where ground-based monitors are around the world. This is basically a relatively publicly available ground-based monitor for which we're able to find a basically year-long measurement somewhere between 2015 and 2019. What I really want you to walk away from this with is that you can see for a large chunk of the world, large swath, there's almost no ground-based monitoring. And this is, one large element of our research is trying to help inform exposures and PM2.5 concentrations in these parts of the world. Even beyond that, however, if you look more closely at the relatively well-monitored areas over North America, Europe, and China, there's an awful lot of white space there, especially if you zoom in. North America has several thousand monitors that are active, but over an area that size, there's still an awful lot of gaps there. If you want to accurately represent the population exposure, capturing those gradients between monitors can be really, really important. An additional element to bear in mind is that this image I've shown here is a more current picture. As you go further back in time, the picture tends to go much more sparse, especially over China, where it essentially drops off entirely if you're looking more around the turn of the millennium. And over Europe, again, much more sparse. North America has been fairly stable over this time period, which is a wonderful resource. But from the global picture, especially that temporal consistency just really is lacking long term. Now, a lot of the strengths of satellite retrievals can complement those limitations in the ground-based monitors. One particular strength of satellite retrievals, of course, they are observationally based. For all intents and purposes, you can consider a satellite instrument as a rather expensive, very well calibrated camera floating in space, taking pictures down below. And because of that, it provides very good spatial coverage. You can see in this image here, this is an image taken over California during the wildfires, I believe it was last year. And what you can really see is this wealth of spatial information, these gradients that are going on where you have these fires and where the smoke's going. The degree of detail there would take an incredible number of ground-based monitors to try and capture. Played out on a global scale in a more annual average sense, I plotted here just an annual average from one of the satellite retrievals, the aerosol optical depth. We'll talk about this metric more on the next slide, but basically this is how satellites essentially view aerosols, one of the main metrics they provide. And if you contrast what you see in this lower image compared to the upper image, you can really see the amount of additional information, at least spatially speaking, that satellites have to offer to our understanding of that distribution of aerosols. And I realized I didn't define aerosols, it hasn't been used before. Of course, aerosols is a more general term of which PM2.5 is a particular component. So there's a relationship there. Now, so satellite remote sensing provides us that spatial information. One of the challenges is they don't directly give us PM2.5. As Jeff mentioned, PM2.5, of course, you're basically measuring the weight, the mass of those fine aerosols in a volume of air. What satellite remote sensing gives us instead, however, is the total column of aerosols. That is, if you kind of added up all the aerosols from the ground all the way to space, and it doesn't give us a mass, it gives us an optical representation. Basically, the amount of light that is extinguished, you can just lost and scattered due to the presence of those aerosols in the air. And so how it does essentially takes images. You see here, this is an image taken over the Indo-Gangetic Plain in India, one of the most polluted areas in the world. You can see this gray smogginess just coated through this heavily populated area. And so what a satellite retrieval does is it compares light that would have been viewed directly from the sun to light that's come through, bounced through the atmosphere, or come through the atmosphere, bounced off the ground and come back up. And by comparing those two within understanding of radio transfer, it can then back out the amount of aerosols that were in the air. Now, there are a couple assumptions that have to go into this. First, you have to make some assumptions about the aerosol size and mass and type, and that affects the way in which it interacts with light. Another major assumption, of course, is this surface reflectance, we call it, basically the amount of light that bounced off the surface. which of course affects what the satellite sees. And there are many different retrieval algorithms that have been developed based on different assumptions or taking advantage of different data sets within that to try and most accurately represent this or to capture this aerosol optical depth. One of the earliest and probably one of the simpler ones to understand is just called dark target. It's still very reliable, very useful retrieval under certain conditions. It basically maybe works under locations where the surface reflectance, typically vegetated areas, can be very well characterized and was relatively dark. It wasn't contributing very much. And if you can get rid of this term, your radio transfer becomes a whole lot easier. You can do this with higher accuracy. And so there's that sort of assumption you can make, or some of them, such as the MAIC and the MISR instrument, as well as retrieval, make use of more multi-angular information to help tease out to make less dependence on the surface reflectance. But there are a lot of different elements you can bring in to try and get the most accurate aerosol optical depth. And the relative strengths and weaknesses of these retrievals come out depending on conditions. And a large part of our work sometimes is actually bringing all these data sets together. I'm not going to talk in great detail about that here today, but there is that element to this too. There are a lot of sources, and bring them together well adds tremendous additional value to the satellite retrievals. But so once you've combined those together and you have that aerosol optical depth, you then have one additional challenge. Aerosol optical depth is not the same as PM2.5. Is that PM2.5 where people are breathing is that mass at the ground that people are breathing. What we have from satellites is this aerosol optical depth, this total column of aerosol in optical framework. And so what our group does is we use a chemical transport model to relate these two quantities. For those of you not familiar with a CTM, basically it's a very complex computer code that combines equations that govern atmospheric chemistry and physics. And it puts into those equations a simulated meteorology and emissions, and basically has this whole simulated atmosphere going on, such as you see animated here a little bit. And so out of this sort of model, you gain a whole wealth of information. You gain insight into chemical composition, you gain insight into the vertical structure of those aerosols, as well as diurnal and sampling effects. There's always a question about satellites, well, they don't always observe. And so within that, you can use this model to help characterize what the impact of those sampling effects might be. Essentially, the end you end up with a ratio of a couple parameters from that model, again, that aerosol depth of PM2.5. And by applying that ratio, you can then convert quite nicely this aerosol depth quite directly into PM2.5. And this is how we produce what we call our geophysical PM2.5 estimates. That is that they're not relying on any ground-based monitors. They just simply are geophysically related via the relationship predicted by GeoChem. And you can see our relative performance on a global scale is quite good. We capture most of the main global features of this than R squared of 0.81. So fairly strong performance just by itself without even bringing in ground-based monitors. Now, of course, ground-based monitors offer an additional source of information. Not only are they good for evaluation, they can also provide insight into how well we're actually doing and into how we can improve upon how well we're doing. And so what we do is we further interpret the differences between the observations on the ground and those geophysical estimates in a statistical framework to add an additional layer onto this data set, essentially incorporating that ground-based information. To give you an idea what that looks like here, I've plotted just the difference between the ground-based monitors and the geophysical estimates of PM2.5 from the satellite-based ones. And if you spend a while looking at this, you begin to see certain features start to pop out. You see, for example, regions with large-scale overestimates or underestimates. You see areas that have much more variability, unlike these areas here, which should be more homogeneous large-scale features. And so what we do is we apply a geographically weighted regression. It's a fairly simple statistical technique, essentially looking for associations between various parameters that we know would impact the quality of those geophysical estimates, and look for associations there so that we can then go ahead and adjust according to the spatial structure we expect to also be associated with each parameter. Example would be speciation, for example, where if we had nitrate emissions or chemistry were misrepresented in the model, that would then affect the quality of our geophysical estimates. And so if we can capture an association with nitrate, we can then go ahead and apply and adjust them accordingly. If you go ahead and do that and apply that adjustment, you can see globally we can gain some significant improvements to our PM2.5 estimates in what we call our hybrid estimates of PM2.5. again, further boosting the agreement and better representing the global structure of PM2.5. Give an idea of what some of those features can look like in terms of that adjustment here. I've just shown quite quickly the adjustment we can apply over North America in this particular case. You can see the combined adjustment here on the side, but perhaps more interestingly, looking at the individual parameters around the perimeter here. For example, to continue to talk about nitrate a little bit, you can see in this particular case, a bias was associated with the presence of nitrate. And you can see, for example, even though we have relatively few monitors over parts of the prairies here, we can have a pretty good guess of what the shape of that bias would look like because of its association with nitrate. For more fine-scale differences, we can have other features driving those biases, such as you can see here, this elevation difference. These are basically looking at things that happen at below the resolution of that geoschem model. So the geoschem model runs at about 50-kilometer resolution. So things can happen inside that, especially if you have mountainous regions, as you see here, where there can be changes in PM2.5 just simply because things are happening at too fine a scale for geochem to represent. And so this sort of association allows us to accommodate and to adjust for those sort of features. And so a real strength of this approach is not only can we do it around the world as a whole, but we can do it regionally and really start to dive into regional concentrations of PM2.5. And here, I don't want to spend a lot of time going through it. I really figure probably most of the audience is most interested in more North American focused analysis, but I did want to just spend a moment to highlight how fortunate we are to live in North America with the air pollution levels that we have. So here in the bottom, I've plotted this is just for January 2018 and July 2018 over Asia and Europe and North America. And what I really want to draw your attention to is this color scale, which changes on each plot. And so if you look over Asia in January, I've set this color scale at 120 micrograms per cubic meter, a very, very high concentration. And even at that level, you can see large parts of the Indo-Gangetic Plain again is completely saturated. You have a month-long exposure for a heavily populated region that is well above, or at least above 100 micrograms per cubic meter. If you look over Europe, you can see I've reduced that color scale down to 30. And if we're talking more in the Western Europe, most regions are well below that. As you get further to the east here, we see large areas are even saturating at that 30 micrograms per cubic meter. Over North America, I've capped at 20 micrograms per cubic meter. You can see by and large, even at 20, the majority, large part of North America in January, July, and throughout the year is well below that threshold. And this comes back to what Jeff was saying at the beginning about how so much of the Canadian population is well below those standards, or at least has historically been below the WHO standard. See, there are, of course, regions within that where there are more high features. You can see here, the San Joaquin Valley in California has very high wintertime pollution, or you can see effects of, say, biomass burning here in Northern Ontario, or again, parts of California in this particular year. So, as I mentioned, one of the real strengths of bringing all these data sets together is having this long time series that's consistent. And what this allows you to do is start to analyze data in some really interesting ways and really insightful ways, both if you're trying to assess a particular cohort that you've been following for a long time period, or just see how certain government initiatives have affected air quality. And so here I've plotted just in the center here, the map plots, you've got, this is just mean PM2.5 concentrations from 2000 to 2004, so the turn of the millennium. And more recently here as well, the same, just an annual mean, or this a 5-year mean PM2.5 concentration, and more recently, we'll just say. If we look at the population-weighted trends over both these regions, over Canada and the US, we see really encouraging signs over this time series. So starting just below 2000, before 2000, sorry, and all the way up to 2020 in this case. You can see if you're looking at the US, you've got concentrations typically ranging at the start of this time series from 12 or 13 to 15 micrograms per cubic meter. And you see this really nice steady decrease over basically year on year, losing about a quarter of a microgram per cubic meter per year over this time series. Canada, by contrast, starts at a much lower concentration at the start of this time series, being around 8 to 10 micrograms per cubic meter, but again, showing some significant improvements over this time period, about half the rate of the US, but considering we start at a lower level, continues to show some great progress there. You can also explore the seasonality of the data set here. So this is just a population-weighted mean PM25 exposure over Canada and the US. You see, broadly speaking, from a population weighted standpoint, both countries show very similar, seasonal variations in PM25 exposure, with peaks in the summer and peaks in the winter. Now, what becomes interesting is you start breaking down a little bit closer, and depending on a particular cohort you might be studying, this could play a real role in what you might be seeing. So if you look at, Canada in particular here in the blue, you see Ontario and Quebec, of course, capturing a large portion of the Canadian population, really follows basically that interannual structure that we talked about for the country. But there's a lot of variation if you had, say, a more maritime or Newfoundland and Labrador-based cohort. Your concentration are decidedly lower, and your summertime peak is relatively higher. Perhaps of particular interest if you're looking more at northern Canada populations, it's a very different cycle in terms of just how incredibly clean you are. It's this wonderful clean environment for most of the year, and then come summertime, your concentrations are rivaling that of more eastern Canada. And of course, every different region has its own story. If you look more in the States, of course, you can see in that San Joaquin Valley feature with those really high concentrations in the winter. And you can spend a lot of time exploring this data set from lots of different angles. And that's really the strength of this data set, is bringing it all together to provide a more complete picture of PM2.5. Now, the same approach, as Jeff was talking about earlier, there's a lot of interest in trying to understand what exactly is driving some of these associations in PM2.5, and what is the role of chemical composition in that. And so using similar tools, we can actually delve into that question a bit deeper and better understand the compositional variation around North America. So a lot of the concepts are very similar to what we've done before. So we start with our hybrid PM2.5 estimates. And we can use GeoChem, that chemical transfer model, to produce an initial estimate of the relative contribution, basically the percentage contribution of different chemical components. For example, nitrate, if we knew it was 50% nitrate at a location, we can just apply that scalar. And this gives us a good initial estimate of composition at a particular location. Similar to what we did with the hybrid estimates for PM2.5, we can then go ahead and compare those geoscience-based estimates to the ground-based monitors of chemical composition. Now, there are less of them, but the same approach works over very large scales, which is really a strength of this. And so in doing that, we can then incorporate that ground-based observation, very similar, looking for associations with particular chemical species and things that may be associated with biases, and can adjust those geoscience-based estimates to produce a high-quality estimate of chemical composition. You get a sense of the agreement over here on the side. So sulfate works very, very nicely with this approach, with an R squared of 0.96. That's the cross-validated in the corner there. And can similarly work for other composite components as well, for nitrate or for organic matter. Organic matter being a bit more difficult, but still quite statistically significant when you're working with it. And once you start asking this question of chemical composition, a whole lot of other questions and details begin to come out of the data set. So for example, here, seasonality can vary quite drastically by chemical component. So on the top here, I've shown this is for spring, summer, fall, and winter. This is a long-term climatological mean for sulfate on the top, for nitrate and organic matter. And what should really jump out at you here is if you just quickly scan across, you can see sulfate has this high peak in the summer, compared with nitrate has this peak in the winter. And so depending what you're looking at for time of year, that peak can be really offset in different times. And if those effects are different, that might explain some of that seasonal differences. Also, of course, for organic matter, again, very different sources going on. You can see, of course, biomass burning, of course, in this particular case, and over here in the northern parts of the prairies and southern part of the territories. But again, you see seasonal effects going on for different chemical components. On top of that, you can also have effects, different trends going on, which could affect particular cohort if you're trying to tease out different values. Different chemical components may have different trends, or different degrees of trends, at least within North America. And so here, similar to before, this is just a spatial plot of PM2.5, SO4, sulfate that is, nitrate, and organic matter for 2000, 2004, from the mid-period and more recently. Population weighted mean is just given here. So 11.5 would be the population weighted mean at the start of this period for all PM2.5. And you can see in all these components, at least for sulfate nitrogen, you see very nice, clear downward trends. Now, but all trends are not equal. And that's captured a little bit nice in this table here. I've given the percentages that different components make up of the population weighted mean PM2.5. So you see sulfate at the start of this period made up about a quarter of the exposure concentrations. And by the end of this time period, down to less than 20%. So you're seeing this different trends going on within a data set if you're considering chemical composition as well. And actually, by the same token, organic matter has not dropped as dramatically, although it has dropped. And so it's actually taking up more by the end of this time series. And of course, if you look at finer and finer regional details, the stories can be different time and time again. And so here we look at over North America. This is just a time plot. This is showing the contribution of each individual component as it changes in time at a monthly time scale. What I really want to draw your attention to here is the sulfate peak. You see every single summer bumping up and down until the end where it almost is basically removed. And this has a lot to do with different government initiatives to help lessen pollution in the atmosphere. And this really is a nice demonstration of how well that's worked. Now, what's interesting is, of course, nitrate hasn't had quite the same progress that way. You can see its wintertime peak is still very much prevalent, but you can see how these can change with time as well. Also, of course, of interest, northern Canada. Again, that really clean environment, which we can really see those spikes associated with organic matter and that those biomass burning events really driving up concentrations most years, depending on the scale of the biomass burning season. Another element to consider when you're trying to represent composition of different regions is how the degree of PM2.5 exposure can actually be a function, can be related to the chemical composition, the relative chemical composition. So what I mean by that is, it can be shown in this plot pretty well. So here we have, for different regions, the population weighted PM2.5 mass, and then the percentage breakdown of that mass at that concentration according to different chemical components. And so, for example, one thing you can take out of this quite clearly is if you're dealing with your cleanest environments, tend to be more heavy on, we'll say, the natural sources. I can see over Atlantic Canada and Northern Canada, if you look at those really clean concentrations here, you have a large contribution from sea salt. And over the States, you see, similar, not near the sea in these cases, but you can see a large contribution from mineral dust. To get to higher concentrations, depending on the region, that composition can change. Over Northern Canada, again, you see a large, if you have high pollution levels, tends to be associated with, in that case, with biomass burning or organic matter. And that can vary in different locations where nitrate often makes up a large proportion as you get to high concentrations in more heavily populated areas. Interestingly, sulfate typically is fairly constant, but then dies out at the highest concentrations as well. This has a lot to do with where population is in those the sources near those heavily polluted areas. Okay, so that's a bit of a whirlwind tour of some things you can look at within the data set and different ways to consider it. Wanted to spend just a little bit of time, and just this one slide really talking a bit about our latest version. So as I mentioned, this is an active area of research for our group. So we're constantly working at this, and every few years we put a new data set. And as I said at the beginning, people are often asking, well, what's the value of the data set? And so I thought it worth talking a little bit about what the new data set offers. Would also mention, as I said before, our group tends to wear two hats. We sometimes focus on the more global aspects of our estimates and trying to improve them. Then we swing back to the more local estimates, more regional over North America. And our latest data set really was focused on trying to bring our global estimates more in line with the quality that we see over our regional estimates of the past. One of the ways in which we did this was trying to improve the fine scale representation. It's perhaps more algorithmic detail I need to get into here, but essentially in certain cases, the fine scale structure is being washed out because of the weightings that were going on. In essence, the different data sets we use have different resolutions. So if you weight towards a coarser data set, you can essentially lose fine structure. So we changed some of our algorithms to help address that. We also introduced a variety of new base predictor variables. I talked about that for incorporating the ground-based monitors. And so we had some other variables we added in there to help improve things in terms of incorporating the ground-based monitors. All in all, it shows tremendous improvements. These are our version numbers at the top here. And so this is our latest version on the side here. The GL in the middle just comes for our global data sets. This is the data set currently hosted by Canoe, just so you're aware. There's our version 4 NA03. This is our previous global value, just over North American comparison. So really what we wanted to do with this analysis improvement was really try and bring up our global estimates so that when compared over North America and other regions, was giving a similar performance to our regional estimates before. And this data set really has quite done that. If anything, the new data set does outperform our old regional estimates under most circumstances. One slight caution I should add to that is our previous data set, we spent a lot of time focusing on really low concentrations. That came out of some of the work that Jeff talked about already, but really trying to understand low concentrations and whether we saw effects at low concentrations and all that kind of thing. The new data set hasn't had that same focus, and there's some indication that like below about 5 micrograms per cubic meter, that this version 4 actually does still outperform, but overall on mass, the new data set is actually still performing over North America and around the world. One major additional element we added to this data set was direct estimates of uncertainty. And so we combined effects we saw with AOD and geographical regression, that again, statistical inclusion and sampling. We brought all those together to produce an estimate of uncertainty, that you see on the side here. And so typically this is for July for monthly based estimate. And what you can see is typically uncertainties from about 1 up to certain regional features get much higher, but generally around 1 to 3 micrograms per cubic meter for per pixel. This is on an individual 0.1 by 0.01 by 0.01 degree, or about 1 kilometer resolution. And of course, you can see features here. This is Salt Lake City and around there, and this is one of the desert regions there, which produce additional uncertainty. What I really want you to walk away from here is the value of aggregating this data. This data set is really intended to be averaged over a certain area. Usually in studies, they average over postal codes, things like that. And this really strengthens this data set. And so here, show a very quick comparison comparing our estimated uncertainty versus what we observe, as just comparing directly at the ground-based observations. And what you can see if we do it like just per pixel, again, uncertainty, we see population weighted uncertainties around 3 micrograms per cubic meter, or 2 observed, since we set on the high end. But as we average that over 10 pixels or 50 pixels, you can see that uncertainty dropping off, roughly following the root of the number of pixels averaged. So really just to encourage users to do spatially averages, such as the data sets that Canoe already provides, really strengthens this data set. Lastly, and very quickly, because I know we're running out of time, I just want to spend a very brief time to acknowledge and to highlight the sort of impact this data set can have, given its coverage in time and space. Jeff already mentioned a little bit about the global burden of disease. So I'm not going to spend much time on that. Again, we're of time here a little bit. But again, identifying PM2.5 is a major contributor to global mortality. The other side we're involved with, of course, are epidemiological studies, looking for associations, trying to understand the impacts that PM2.5 is having. One of the more interesting recent ones has been association with COVID-19, the severity of the reaction to COVID-19. Using data set like ours, actually using ours, we're able to identify that pollution levels, PM2.5 exposure was actually causing, or is associated with, more severe reactions to COVID-19. But even ranging from diabetes, dementia, birth outcomes, looking at maternal effects that way, and of course the low PM2.5 effects we've already talked about a little bit. I will probably leave it at that. I'm aware we're basically out of time, but I just wanted to give you a very quick whirlwind tour of the sort of things you can do with this data set, hopefully give some insight of things to consider. If you have any questions, feel free to contact me. And yeah, hopefully that gave you some things to think about. So thank you.
Great, thanks, Aaron and Jeff, for that really jam-packed and informative presentation. If there are any questions, please feel free to put them in the chat. You can stay, I think, a few minutes more if people do have questions. Question for Aaron. Canoe distributes 3 different versions of PM 2.5 estimates developed by your group. You showed increase R squared in more recent data sets. Are there certain instances where the older data sets would be more quote unquote appropriate?
Generally speaking, I would say you're best to go with the most recent version provided by Canoe. There are a few features that people have commented on between probably the first and second versions hosted by Canoe, but by the version 4 NA03, which is the most recent hosted by Canoe, they're pretty much aligned, and it's basically just a better data set than the earlier versions that Canoe currently hosts.
Great. Well, if there are no more questions, I think that's probably a good place to end. So thank you again very much, Aaron and Jeff, for your presentation and taking time to speak with us today for our webinar. I think it was really, really informative. And for everyone else, have a great afternoon. We'll send a follow-up email with the recording of today's presentation as well.